Hi, everybody. At this point, you should have watched the two AP Classroom videos introducing this idea of estimating areas under the curve or under curved functions. Those videos go to a little bit of application of why we want to do that, and I'm going to do that here in a second as well. Here, I would like you to take notes with some of the examples that we're doing, and there might be time where you might pause the video here so you can make sure you've got some of the examples down for the problems that I'm going to ask you to do here soon. So this is second half of calculus we're entering into. This is 5.1, estimating with five finite sums. It's very easy in this diagram to find the area underneath of that rectangle or of that constant function at 12 with a big rectangle. If the velocity function was curved, trying to find the area underneath of that is a little bit more difficult. The AP videos didn't go into how to do a systematic area underneath. They did do a rectangle and a big triangle, but I think we can do better than that. So here we go. All right, so let's consider, again, one more time, an example of why we'd want to do this. So let's say an object has a constant rate of 3 feet per second. So this is its velocity, and it's a constant velocity, so zero acceleration. We know that rate times time equals distance. So after 4 seconds, if I'm going 3 feet per second, I obviously would have gone 12 feet. Well, we can see that, and we would know that from our distance equals rate times time equation. But if I graph this constant function of just 3, so there's my velocity function, 3 feet per second, over the span of time of 4 seconds, well, the area underneath of it actually represents the displacement, or the distance traveled in this case, because there's no change in direction. And we can prove that through the units. So if I take 3 feet per second, which is my constant velocity, times 4 seconds, well, both of those units of seconds would cancel out, and I would just get 3 times 4 feet, or 12 feet. But what happens when the velocity is not constant, or even not linear? What if it's curved? Well, the area underneath of it is still going to represent the displacement, or the distance that you've traveled. For instance, if I have this velocity equation, so 1/8 t squared plus 1, this is not a big 4 equation. Big 4, our velocity equations are linear. So clearly we can see we're going beyond what we've done in physics with our kinematics. We can estimate the area under the curve instead of using big rectangle and triangles like they did in the video. What if we just do rectangles? So we're going to first do what's called the left-hand rectangular approximation method. I would at least maybe do the diagram and the calculation in your notes here so you have this visual to go with it. So I'm going to make a little table of values, t values and my velocity values. And I'm going to try to approximate the area underneath of this curve from 0 to 4, making 4 rectangles. All right, so here we go. To get my first rectangle, I'm going to find the height of the function at 0. And the value of the function at 0 is 1/8 t 0 squared plus 1 is a height of 1. So, and I'm going to make a rectangle. And now the rectangle has a width of 1, so the area of that rectangle is just going to be 1. And this is picking the left value of the function. So this interval is between 0 and 1. And I'm going to pick the left side of the function, its function value, where it comes up and hits the function. That'll determine the height. So let's look at the next example. So my next rectangle is going from 1 to 2. I'm going to find the value of the function at 1, the value on the left side, and putting 1 into my velocity equation, 1/8 times 1 squared plus 1, that's 1 and 1/8. So you can see I'm coming up and I'm drawing my rectangle so it hits the function at 1, make a rectangle straight across, and then it also has a width of 1, so the area inside of that rectangle is 1 and 1/8 times 1, or 1 and 1/8. And we keep going. From 2 to 3, I'm going to find the height of the function at 2. So 2 into my velocity equation is 1.5. And so the area of that rectangle is also 1.5 because the width was a width of 1 and 1 more. Between 3 and 4, I'm going to determine the height at 3. Height was 2 1/8 times a width of 1. So 2 1/8. And then we want to sum them up. Finding all of those 4 areas, adding them together is 5 3/4, 5.75. So the question is this the actual area under the curve? And of course not. We can see there's these big blank spaces, which frankly one could argue, hey, can't I draw make little triangles inside of there? Yeah, I could do triangles inside of there, but we'll see in a second, maybe that's not the most efficient way to do this problem. So at this point, my left-hand rectangular method, picking values on the left side of each interval, comes out to 5 3/4. So begs the question, what happens if I go from the right? So now let's do a right rectangular method. Again, any point in time, if I'm going too fast, just make sure that you pause. So now I'm going to be making rectangles coming on the right-hand side. So some of these values I had already determined. So at the value of the function at 1 come up and I hit the function, that's where I'm going to make my rectangle. And that was 1 1/8. So the only new one over here is the value of the function at 4. So 4 squared is 16 times 1/8 is 2. 2 plus 1 is 3. The height of the function right here is 3. So that's how tall my rectangle is with a width of 1. And then I'm going to add those all together and I get 7.75. That's 2 units more than what my left-hand rectangular method was. And how accurate is this? Well, you can see now I've got more than what I need. This is an overestimate. And we'll talk later on about what constitutes an over or an underestimate and how to predict whether or not it's going to be. But clearly I can see my rectangles are over top. This is more area than what I need. So one could say, how could I get any better? Well, what some people will argue is maybe you can average the two, the left-hand rectangular method and the right-hand rectangular method together. So, but that means doing both of those methods separately. Maybe there might be a better way, and it is. What if instead of picking a point on the left or a point on the right, what if I pick a point right in the middle of each of the little intervals? So this is going to be called a midpoint rectangular method. So now I do need some new values. So I'm making a new table here. So I'm going to first need to find the height of the function at 1/2. So I'm going to put 1/2 into my my velocity equation. So 1/2 squared times 1/8 plus 1. I get this decimal, and you can work with the fractions, but I'll use the decimal approximations. And you can see when I come up and draw the rectangle this time, part of it is above and part of it is below. So they're almost kind of canceling each other out. Now, do they fully cancel each other out? No, because of the curve, you know, the area underneath you can see is going to be a little bit less than the area that's not calculated in this white region. So it's still not exact, but at least it's getting us a closer approximation. So now find the height at 1.5. Substituting 1.5 into my function gives me a height of 1.2815. But again, remember there's a width of 1, so I'm really multiplying that height based upon the function value at the midpoint times the width. And again, you can pause me at this point and go and calculate the other ones and then join back in. 2.5 is a height of 1.78125, and then at 3.5, and then I'm going to add all of those up, and I get 6.625. Yeah, kind of in between the 5 3/4 and the 7 3/4, kind of in between there. Not exactly the average of the two because of the curved nature of this graph, but probably gives us our best approximation to date at this point, because these areas above and these areas below almost cancel each other out. So this is a really good approximation. So the question is, what could I do to better the approximation? Well, I can make more rectangles. Again, I would only want to go from 0 to 4 because that would be my time that I'm trying to find displacement of, but maybe I'll make my widths of my rectangles smaller. So instead of putting in 4 rectangles, maybe I'll put in 8 by making each of the rectangles a width of 1/2. So more rectangles is going to fill in more of that area under the curve itself. So what if I do go to 8 subintervals? So I'll make my table. So now I'm going to figure out, this is with a midpoint. I'm still sticking with midpoint. So my first interval goes from 0 to 1/2. but then the midpoint of that interval is a quarter. So I'm going to figure out the value of the function at a quarter, and it's just putting them into the equation. Now my next interval is from 1/2 to 1, so the midpoint of that is 3/4, 0.75. Find the value of the height of the function there, and I keep going and going and going. So now I have 8 rectangles, each of those little areas canceling each other out. Now, here's a little cheaty method. At this point, I know each of these rectangles' heights, all of their widths are now 1/2, so I should have been taking the first height times 1/2, the second height times 1/2, the third height times 1/2. Well, why don't I just sum them all up and then multiply by 1/2, because they all have equal subintervals. They won't always, but in this case they do. And I get 6.65. So that seems a little bit more accurate. Now, eventually we're gonna get to the point where we're gonna try to figure out the exact area under the curve. How would I think I would do that? Well, to get more and more exact, I would want skinnier and skinnier rectangles. In fact, I would want the number of the rectangles to approach infinity, or the width of the rectangles to approach 0. That is going to be our way of actually calculating the exact area under the curve. And if you can think about a calc concept there, approaching infinite number of rectangles or approaching a width of 0, yeah, limits are going to come back. We're going to talk about limits, but that's for another day. The actual full exact answer of the full area underneath of this curve, all of the area exactly is 6 2/3. And we'll figure out that method coming up. But for now, we're going to do approximations. One thing to mention before one more example is that sometimes we might see combinations of both methods, left and right. So if I say I have inscribed rectangles, the rectangles are all below the function. So I might have a combination of LRAMs. The first two are LRAMs. The next one, the third rectangle, is either L or an R. It looks like it's straddling maybe that vertex. But then I'm switching over to a right rectangular method. And again, vice versa for circumscribed rectangles, those all lie above. So it is possible to have combinations of left and right and midpoint, depending upon if I'm inscribed or circumscribed. That's not a common thing done on the AP exam. The left, right, and midpoints definitely are. So let's get to one final example here that I'm gonna have you do and have you pause as we go. So new function, x cubed on the interval from 2 to 10, and I wanna make 4 subintervals. So when we do these problems, you'll have to be given the function, the interval, and the number of subintervals for us all to get the same answer. Obviously, if you make more subintervals, you get a more accurate calculation, but let's all be on the same page here. So if you think about it already, the width of the entire interval is 8. From 2 to 10 is a width of 8. And if I'm squeezing 4 subintervals in there, that means each rectangle is going to be a width of 2. So keep that in mind. And we might want to, and I'm going to draw a picture here in a second. So what I did is I went into my calculator and I went into table set above window, and I turned on the independent variable to ask. And I just put in the values that I wanted. I know I'm going to do a calculation at 2, the far left value of the interval, and then I'm going to go every 2, because I know my width of my rectangles are going to be 2. So 2, 4, 6, 8, and 10. So I've got all my numbers at my disposal ready to go. So let's do an LRAM first. So here's a picture of what the LRAM would look like. So I'm going to find the height at 2, the left value of that first interval. Then my next rectangle, I'm going to find the height at 4. That's the left side of that rectangle, and so on and so forth. So an LRAM is going to be a width of 2 times the value of the function at 2, plus a width of 2 times the value of the function of 4, and then the same at 6 and at 8. And then at that point, I'm just going to pull values from a table. And so 2 times 8, 2 times 64, 2 times 216, and 2 times 512. Notice I'm not using the 1,000 because that's on the right side of my last interval. I've got it there for later. And as I've said before, you do not need to simplify these answers. You can add this up. It comes out to be 1,600, but I don't need you to add these up. In fact, on the AP exam, you definitely don't want to add these up. Okay, I'm going to pause here, or I want you to pause here, and I want you to do an RRAM, a right rectangular method. So it's up to you if you want to draw it, but at this point, I think you should maybe be able to know the 4 rectangles that you're going to be drawing for a right rectangular method. So pause me and do the RRAM. Okay, here's what the picture would look like with an RRAM. These is going to be overestimates. So coming here on the right, and I can still use that same table. So now my first rectangle is going to be figured out with a height at 4, whatever the value of the function is of 4, that's how tall my rectangle is. And then at 6, and then at 8, and then at 10. And grabbing values from my table. And again, don't have to add that up, but that is now jumping all the way to 3,584 from 1,600. It's because when I get up to 10, 10 cubed is 1,000, there's going to be a lot of overestimated space on that last rectangle that's up off the screen. All right, one last one. I want you to pause me here, and now I want you to do an MRAM, which means you're going to need a new table or new values in your table. You can now just keep, if you switched your calculator, as I said, you're now going to have to figure out some new values here. So go ahead and pause me and try an MRAM, which should be a better approximation of the two. All right, now I redid my table with all the in-between values and my new graph. So now my first height is going to be determined at the midpoint between 2 and 4, which is 3. So I've got my height at 3, at 5, at 7, and at 9. And those are what I'm going to then substitute in and grab those values from my table. And I get 2,448. Again, don't need to add it up, but at least we know it should have been between the two. And again, these areas don't cancel each other out. The little rectangle, triangle-y looking shape above and the triangle-y looking shape below, they aren't triangles because of the curved nature of the graph, but they cancel out most of the area between both of those. All right, so here's your introduction to areas under the curve. There's a couple practice problems. All right, good luck.